Welcome back to 6612. In today's lecture, I'm going to cover asymptotic properties of MLEs. So in last lecture, we covered maximum likelihood estimation and how to do it for a couple exponential family distributions. And today we're going to cover the asymptotic properties of those MLEs and the observed and expected Fischer. So the exact distribution of maximum likelihood estimators can be very complicated. So often we have to rely on large sample methods instead of getting things like confidence intervals or variance of estimators directly. And these large sample methods ensure that as your sample size gets bigger, your parameter estimate based on the MLE gets closer to the true value and its variability decreases. The first asymptotic property is the property of consistency. So here, theta hat n is the MLE estimator when sample size is n, and theta 0 is the true value of that parameter theta. And what this basically says is that this estimator converges in probability to the true value, meaning that as n gets larger, this ensures that your estimator MLE of theta is getting closer and closer to the true value of theta. I would say the most important asymptotic property is that of asymptotic normality. And what this assures is that, again, as sample size gets larger and larger towards infinity, the distribution of your estimator approaches a normal distribution after it's been centered and scaled properly. And this is going to be really useful for obtaining things like confidence intervals and doing hypothesis tests in the next lecture. And then finally, there's asymptotic efficiency. And what this means is that of all possible estimators of theta, your theta hat MLE has the small. And if you're taking theory this year, you're going to prove all of these properties. I'm not going to go into these details or really test you on them. But we do need to know that these properties exist and why. Well, the reason why is that without asymptotics, we can't really make any inference about the estimators. Without asymptotics, we can't really make any without asymptotics, we can't really draw any conclusions about the population we're trying to understand using our estimators. In particular, asymptotics show us that our point estimates, our MLEs, actually are converging to the true value as sample size gets larger. They also allow you to get confidence intervals around those estimators, and allow you to do hypothesis tests and get p-values as well. We talked a little bit about the Fischer information in the previous lecture. And luckily, we can use this to calculate the approximate variance of our estimator theta. So you can see here that I'm calling the asymptotic variance var hat of theta hat. And you might be wondering why so we put a hat on the estimator to denote that this is an estimate of the true value theta, but it's not equal to the true value. And similarly for the variance here, we're putting a hat on that because this is the asymptotic variance, meaning as n increases to infinity, this is going to be the true variance. But right now, when your sample size is finite, which it always is going to be in practice, this is just an estimate of that true variance. It's not equal to the true variance. It approximates it. So we can calculate this asymptotic variance using the Fischer information. And there are, in fact, two different versions of the Fischer information. And for the record, I'm going to use information and Fischer information interchangeably throughout this lecture. Information is the second derivative, the second derivative of the log likelihood with respect to the parameter theta. You have the expected information is here. That's when you take the expectation of that quantity of the second derivative of the log likelihood, and then the observed information is just the same thing but without that expectation around it. And both of these, both the expected information and the observed information, if you take the inverse of these values, they give you an asymptotic estimate of the variance of theta. And so one of the ways that I sort of remember this is that we call it the information because as n increases, the information increases, meaning what you know about theta increases. And the variance is just the inverse of the information. So as information increases and n is increasing, then the variance is decreasing. So a little bit more about the observed versus the expected information. So in general, estimates of variance calculated either using the observed or the expected information are similar for sufficiently large sample sizes. And in fact, the observed converges in probability to the expected information. However, in the cases that we're going to look at for GLMs, these quantities are actually identical. And I'm going to show you that shortly. But in the case, however, in situations where they're not exactly equal, if you're curious, there's a nice paper from 1978 that argues that in general, better variance estimates are obtained using the observed information. And that's nice because typically the observed is easier to compute as well. So here I'm going to show you an example of how to actually calculate the Fischer information using our favorite distribution, the Bernoulli distribution. So I'm going to calculate this using the expected information, but then I'll show you an observed example in the next couple slides, and you'll see that they're equivalent. So the Fischer information, the expected Fischer information is, which I'm going to call I of pi here, is the negative expectation of the second derivative of the log likelihood. And luckily, last time we calculated some of these values, but and so we know that this is equal to the negative expectation of the derivative with respect to pi of the quantity square root of yi over n, square root of yi over pi minus n minus square root of yi over 1 minus pi. And this quantity in the middle here comes from the log likelihood of the Bernoulli distribution, which we calculated in the last lecture. So that's where we're getting that. And so if we take the derivative of that quantity, what we get inside the expectation is negative square root yi over pi squared minus n minus yi times 1 over 1 minus pi squared, and they're going to actually get two negatives there, so they'll cancel out. One coming from inside this 1 minus pi and one from and you can, this negative you can take out of both of these and then use that to cancel out this one here, and so all of these are going to be a positive. And then what you can do is you can actually distribute the expectation, so you get that's equal to the expectation of the sum of yi over pi squared plus the sum expectation n minus the sum of yi over 1 minus pi squared and then for independent variables you can actually pull that summation out and pull the expectation in, giving you the sum of I of the expectation of yi over pi squared plus n minus the sum of the expectation of yi over 1 minus pi squared. And because this is Bernoulli distribution, we know that the expectation of yi is equal to pi. So that's gonna, you can plug that in with a pi there, and that in with a pi there. And then just going to the next page, what you get is pi over, so n pi over pi squared plus n minus n pi over 1 minus pi squared, which simplifies to n over pi plus n over 1 minus pi, which further simplifies to n over pi times 1 minus pi. Okay, so that's the expected information I of pi. And so to get the actual variance, what you want, the asymptotic. So to get the actual asymptotic variance, what you want is their estimated variance of estimated pi is equal to this expectation. The inverse of this, is the inverse of this expected information evaluated at the quantity pi hat. So to get that, what we'll do is we'll take our 1 over our calculated information and then plug in the value of pi hat, which is the MLE. That's equal to pi times 1 minus pi over n. Pi equals pi hat, which is equal to pi hat times 1 minus pi hat over n. And so there is your asymptotic variance calculation for the Bernoulli distribution based on the expected Fischer information. And as you can see, this quantity, this variance quantity, will get smaller as n increases. The sample size gets larger. Yep, here's our solution. So I just want to show you that in the case of the observed information for the Bernoulli distribution, you actually get the same answer when you get the variance using the observed information rather than the expected information. And so this first line just gives you the equation for the variance calculated using the observed information, plugging in the log likelihood, so that plugging in the second derivative of the log likelihood here is what happens in this second step. And you're going to want to evaluate that at theta equals theta hat. And so you plug in theta hat for this bottom pi here, but I've also plugged in theta hat and for this sum yi, because this, since theta hat is equal to the sum of yi over n, you can actually substitute n times pi hat equals the sum of yi. So that's actually what's happening between this step here and this third step here. We're substituting this yi, some yi for the n pi hat, and then down below we're substituting pi for pi hat because we're evaluating this observed information at pi equals pi hat. And because of that, you get some cancellations here. This will cancel out, that will cancel out. This reduces to n times 1 minus pi hat, which will cancel with the one on the bottom. And you're left with this quantity here, which in fact was the same quantity that we calculated using the expected information. Great, and so that's all of this for this lecture on asymptotic properties of MLEs. In the next lecture, we're going to look more into in the next lecture, we're going to look into some hypothesis testing using these properties.